Good morning all. So, today we will continue our fourth lectures. So, we have already covered the introductory section of the analog electronics and we started discussing the bipolar junction transistor, right, BJT. So, to start with, this is your device structure. For example, for NPN this is emitter, base and collector, right, and this is the current convention, right. So, emitter current is collector current plus base current, which is consisting both majority carriers and minority carriers, and this is actually your device structure. So, this is your collector which is covering both emitter and base is sandwiched between emitter and collector. So, generally this collector base junction is reverse biased and emitter base junction is forward biased, right. And because IB is so small, we can have an amplification in the collector current. So, this is our large signal model. So, what is the large signal model? If you think of this collector and emitter, we can think that this base and emitter junction is forward biased, right. So, we just assume that there is a diode, right. So, this diode is the base emitter junction, and between collector to emitter what we are thinking, as if a current source is there which is deriving this IC, right, which is an amplified version of this IB. Okay. So, output side, so input side what we will model? Input side we will just model like a diode, clear, and output side how we will model? Just like a dependent current source. So, you know what is the equivalent symbol of a current source? A current symbol and its output resistance should be in series or parallel? Parallel, right. Okay. So, input side we have a equivalent PN junction diode, because this base is P type, right, NPN. So, this is P, this is N, this is also NPN, right. So, this is my equivalent large signal model. Large signal means complete current we are considering. When we will be considering small signal model, we will be considering only the AC current, not the DC current. DC portion we will assume that not there. Okay. So, this is our model. Now, input side we can either do in terms of base emitter voltage or do in terms of base current. So, for example, here output current is expressed in terms of base emitter voltage, IC is equal to Is exponential VBE by Vt. Okay. But here output current is written in terms of base current, IC is equal to beta IB. So, both ways we can write, and this is our plot, right, IC versus VCE, right, for different values of what? IB. So, you think of this way that I am varying the base voltage also. If I vary base voltage, what will happen? Base current will vary. If base current is varying, what will happen? IC will vary. So, I have three variable actually. What I am doing? Input side I am varying base voltage or base current. In this x axis I am varying what? VCE. Then I am getting the total plot. If I have a fixed VB, then I will get only one plot. Okay. But as I am varying this base voltage also, so on this y axis also IC is also having several plots, clear. So, which region you know, if your base voltage is less than cutoff voltage, then it is in cutoff, right, IB and IC is equal to 0, this is cutoff. and when both of them are in saturation, both of the junction, then it is saturation region, and forward this base emitter is forward and other collector base is reverse, then this is in active region, right. Now, see in this forward region, this saturation region, what is my incremental beta? You see current is very low, na. If this is in this flat region, my current is maximum, right. So, beta is also maximum. In this region, my current is maximum, right. So, beta is also maximum in the active region, but in the saturation you see current value is less. Okay. So, this in this saturation region, my beta value is different than the active region. Okay. This is called force beta or saturation beta, and its value is less than the actual beta, clear. And also you see in this region and in this region where the resistance is maximum, if it is flat resistance is maximum, na. Okay. Because you are getting del Vc, but del Ic is 0. So, ideally this is very high, but this region you see you have a slope of 1 by RC saturation, right. This is a transconductance slope del Ic by del Vc. So, if you inverse it, you will get the resistance at the saturation region, and this resistance is also very small. You see this resistance, the slope at this saturation region, this provides a small saturation resistance. Now, these are the different operating regions. We have two junction, one is collector base junction and another is emitter base junction, right. So, we have a emitter base junction and we have a collector base junction, clear. Now, cutoff and saturation, these two, the BJT can work as a what? Switch, and in this region it will behave like a BJT can behave like an amplifier. Okay. So, in this analog class we are interested about this zone, which zone? Active region. Okay. And this other zone inverse active, this is not that important. So, mainly we will be thinking about emitter base junction as forward biased and collector base junction as reverse biased. So, can you tell me, if this is forward bias, the base voltage should be at least how much voltage above the emitter junction? 0.5 to 0.7, right. 0.5 to 0.7, if it is above this emitter voltage, we will consider that this is forward biased, and this is N, this is P. To make this collector base reverse biased, the collector potential should be higher or lower? Higher than the base potential, right. Okay. So, this should be high and this should be around 0.7, and if it is at 0, this should be at 0, this should be at 0.7, and this should be higher than 0.7, right. So, when this potential goes down, after which potential we will say that it is entering in saturation? Vc is at, if it is falling and if it is falls below 0.3 volt, then we will say that it is entering in, both are forward bias. Okay. So, at forward bias, what should be this maximum voltage? 0.3 or 0.2. Okay. So, in this active region, this is behaving like an amplifier, other two region it can behave like a switch. Now, this is my symbol and current convention, and this is the emitter current expression. So, if we want to bias the NPN transistor, I should provide a base emitter voltage, right, okay, so that the base and emitter is forward biased. And I also provide a positive voltage between collector and base, so that collector and base is reverse biased. So, this is my general biasing. If I do this, then what will happen? I will get a base current, I will get a amplified collector current, and sum of these two, IE is equal to IB plus IC. Okay. And as we know that this current is exponential in nature. So, this current that depends exponentially on the excitation voltage. Okay. So, and this is our, this is a constant, this we call this as saturation current, right. So, IE is equal to IES exponential VB by VT minus 1. Okay. So, this is our diode current model, and this is the amplified emitter current. Okay. Similarly, in the PNP transistor also we can have the connections, but in emitter PNP junction what will happen? The emitter will be at the higher potential. Okay. This will be just complementary to the NPN. So, in this emitter is at lower potential, in this emitter will be at the higher potential, but the basic concept will remain the same. Okay. And the saturation current generally is very small, ranges from picoampere to femtoampere. So, I said if we have an current IC and we have an base emitter voltage, so how they are related? Exponentially, right. So, if you want to plot the input voltage VBE and collector current or base current, their nature will be exponential. Okay. So, this is your expression, IC is equal to IS exponential VBE by VT, right. What is VT? VT is known as thermal voltage, right. Expression K is Boltzmann constant, KT by Q, T is temperature in Kelvin and Q is charge of an electron. Okay. So, at room temperature this is roughly equal to 25 millivolt. Okay. So, we get one expression of IC, then what will be the expression of IB? I will divide this by beta. So, I will divide this by beta. Now, there is a relationship between IC and IE, that is IC is equal to, generally we tell it alpha, right. And can you tell me what should be this value of alpha? Which one is higher, IC or IE? IE is higher, and value of IB is small, very small, right. So, IC and IE they are very nearly same, right. So, this alpha should be nearly close to 0.9, close to 1, close to unity, but it is less than 1. Why? Because this is higher. Okay. So, these three are, if you remember these two relationship, then you can find out the relationship between alpha and beta. So, if you remember that alpha is just less than 1, 0.99, so you can find out alpha is equal to beta by beta plus 1. Okay. From this relationship you can, if one is given, other you can calculate. Now, this expression you also know, what is this? Early voltage. How this is formed or what is the explanation, why this is happening? Base width modulation, right. Effective base width is decreasing. You understand that? See, ideally this current should be flat, right. Ideally this current is flat. Here what is happening? Collector potential is increasing, right. So, if collector potential is increasing, this collector and base junction they are becoming which region, which bias? reverse biased, right. Collector and base is reverse biased. Collector potential as it is increasing, so my reverse, if reverse bias is increasing, what will increase? Depletion region. You know depletion region, that there is no charge, right. So, only the immovable ion is there, right. So, between collector and base, if this depletion width, if you increase this collector potential, what will happen? This depletion width will keep on increasing, right. So, effectively what will happen? This base junction as if it is getting thinner, right. Okay. So, in terms what will happen? This your collector current will increase, okay. And if you increase this potential, they will short at the this voltage, which is termed as the early voltage. Okay. So, this slope is dependent on this early voltage. Okay. If you have a flat zone, this is ideally you have a infinite resistance, right. Otherwise, because of this early effect, you will be having early voltage and this resistance. Okay. So, why this is happening? That the base width is changing as Vc is increasing. This is known as the base width modulation. And typical value of this early voltage is around 50 volt to 100 volt. So, the graphical analysis that we discussed before, same we will start. So, what we are doing? See, first we have to make sure that this transistor is working is in proper bias. What is the proper bias we have defined? Active region. To make it active region, we have to give a, first we have to give a DC value, right. So, that its base emitter is on. So, this is first we will do, we will provide a DC voltage at the base. Next what we will do? We will provide a DC voltage at the collector, okay. And by default this is the source voltage or supply voltage VCC, clear. Next is what? Emitter junction is connected to a lowest potential. So, all these three are my DC connections, right. Then what we will do? Then we will check that, okay, let us vary this base emitter voltage and plot the IB. So, we did that, okay. And this through this resistance also one current will vary. If we vary this potential, then this current will also vary, right. So, you see the same current that is flowing through the resistance, that will also flow through the base, right. But the nature of the current flowing through the resistance and the nature of the base current, are they same? They are not same, right. So, they are like this, that one current is like this exponential in nature, other current is following ohmic law. But what your KCL is saying, that IR should be IB. So, they have to have the same value, right. Both of the plots are different, but where they are same? This point, right, at the point of intersection. So, this is my solution, right. So, this way of calculating the value is known as the graphical way of solving the equation, right. I can equate these two and get the value. I have a expression V is equal to IR, right, ohmic law. From this I get a one equation, and IB is equal to IS by beta exponential VB by VT. From there I will get another equation, and solving these two, putting one value into another, we will get the IB value, right. So, this is a mathematical way. What is graphical way? Where they are cutting, that is my solution. okay, and this ohmic expression is known as the load line, clear. So, this is my DC value of IB. So, sometimes as it is we termed is that as a Q point, quiescent point. So, this is my IBQ and this is my VBQ. Okay. So, where we will bias? We will make this voltage fixed at this voltage. Okay. We will make this VCC such that this IB and IC value is fixed at this point. This is the meaning of DC biasing. So, this is in the input side, right, and what is the expression? You see, if I do a KVL here, suppose AC voltage is not there. Okay. So, VBB is equal to drop at this resistance, VBB is equal to IBRB plus base emitter junction. Okay. So, from this I can calculate IB, clear. So, you see, when this IB is maximum, when VB is equal to 0. So, VB is equal to 0, IB is maximum, this point. What is that point? VBB by RB. What is the minimum point of IB when VB is equal to VBB? Current is 0. So, if you get these two extreme point, then you can connect them and draw the load line. Okay. So, how to draw the load line? You find the expression of the current, then figure out 2 points, maximum point, minimum point, connect them, where it is intersecting the actual graph, that is your Q point. Let us see it in the output side, then it will be more clear. Now, see this, so many IB is possible, right, right. In previous case we have selected one IB, right. Similarly, I can have several IBs. Okay. Why? Because if we have different VBB, then we can have different IB and they will intersect with this and we can have different Q. Now, if we have multiple Q, then we have to again select that, okay, among these many Q, which Q is best, right. So, what we discussed, that which Q you should select, which is at the middle. Why? Then you have room at the upper side as well as the lower side. Okay. So, if you want to amplify any signal, it can, before getting saturated, saturated means this is flat, right. So, current cannot increase from this point to this point, current can increase, right, but here it is maximum. So, it will get clipped. Similarly, from this side to this side there is a room. So, if IB is varying from this point to this point, IC will also have a room to vary, but after this point it cannot go, right, it will be 0. So, similarly for this output side we will find a equation for IC. What is the equation for IC? You see, we will do a KCL here, a KVL here. VCC is equal to this drop plus this potential, collected to emitter, one potential should be there. So, what is this total voltage? The drop across RC plus the drop across VCE. So, IC is equal to this expression. So, when IC will be maximum? VC is equal to 0. What is the value? VCC by RC, this is your that point. And what is the minimum? 0, right, when VC is equal to, in other way what we can say, that suppose this BJT is in cutoff mode. Cutoff mode means suppose base emitter junction is 0, IB current is equal to 0, IC current is equal to 0. So, VCC minus ICRC, this drop is 0. So, this potential will be VCC. So, this is my load line, and what is the slope? minus 1 by RC. So, this could all the intersection could be my possible solution. Among this possible solution, which DC value we should choose? This middle value we should choose. So, this is my Q, VC Q and IC Q. So, what is the meaning of DC biasing? We should select a proper value of VBB to get a proper value of VCQ and proper value of ICQ. So, now you are ready to add a signal source. After this DC is complete and you are satisfied with your Q point selection, then what will happen? So, this DC is done. Now, you will add a small voltage, so that you get a amplification, right. So, if you see that, say that this is my VB and this is a small voltage source. Due to this small voltage source, what will happen? You will have a small input current IB. If your V is increasing, what will happen? IB will also increase. If IB is increased, what will happen? IC will also increase. If IC is increased, what will happen to your V0? Increase or decrease? See, what is my output? This is my output. Okay. This output is also equal to VC. So, what is my V out? This is equal to VCE, and what is the equation? VCC minus ICRC. So, if your IC is increasing, this subtraction will decrease, right. So, if my input voltage is increasing, IB will increase. If IB is increasing, IC will increase. If IC is increasing, ICRC will increase. If ICRC is increasing, this will decrease. So, this is in positive phase or negative phase, out of phase or same phase, out of phase, right. Input is increasing, output will amplify it, but it will in the 180 degree phase shift. Okay. So, if my input is going like this, my output will be going like this, inverting relationship, right. Why? Because of this. If you take a derivative of this, what you get? Minus sign, right. This derivative will go 0. So, it will be, suppose you want to get a AV, del V 0 by del V in is equal to minus del IC by del V in into RC. What is del I by del V? Transconductance. So, this is my transconductance if I term it as GM. So, this is my gain. This gain is large signal or small signal? This is small signal gain. This AC signal is small signal, no? And you see this DC term is derivative, if you do derivative this is 0. So, this is only containing the AC signal. So, are you sure about this load line? What is load line and how to get the Q point, that we have understood. And this equation is simple KVL. Now, this is your amplification that we are discussing from so many days. This is your which current? Input current. What is your input side? Base. So, this is your IB. This is your input voltage VBE. Now, you are plotting IB versus VBE, you get a exponential plot. You have drawn the load line, you got the Q point. Now, what this is trying to say, that if we have a small region, you see this graph is exponential in nature, but if you cut into a very small zone, that you can approximate as a straight line. Okay. Just to remember about your calculus. What we do, that even if a signal is nonlinear in nature, a small portion we can always think of as a linear. Okay. So, how we are approximating? See, what is our objective? Our objective to make it as simple as possible. Okay. Now, in general BJT is nonlinear device, the current nature is exponential. Now, how we are approximated to a linear equation? We are assuming that this is a very small portion, right. So, what is the first condition? That within this small portion, if your input is varying, now this VB, this small VB is your AC signal. Okay. First what you did? You gave a DC potential, DC biasing. On top of this, now you are providing a AC signal, and what is the condition? This AC signal should be small. Why small? Because this graph we are considering a small section, so that we can approximate it as a straight line, okay. Or we can utilize the linearity, so that superposition all this is available and it will be easier to calculate. Okay. So, that we have done. So, now what they are saying, that if we vary a small VB, we will get a small variation in the IB, right, and because of that we know that IC is equal to beta IB. So, how this is varying, you just follow. My VB is my input source, I am varying that. Because of that IB is varying. So, this is at the input side. Now, because of that at the output side what is happening? IC is also varying, and if IC get varied, what will happen? My output voltage will also vary, and because of this beta I will get a amplified version of output. Clear? So, now you see at the output side what we are doing? Because of this variation, now my output current is also varying, IC, and if IC is varied, my VC will also vary, and this VC is my output. So, just step by step you are thinking, then you think, then you will understand how this amplification is happening, and you make it, always make it think in a simple way. So, this is my complete biasing. In previous circuit you see I have used a voltage source, right, VBB, to bias it. I have used a DC source, VCC. Now, always try to reduce the number of sources. This source you cannot go without VCC, right, VCC you will be always needing, right, supply voltage you will be always required. So, if we can replace this VBB, then it is better, right. We should reduce the less number of voltage source. If we have several voltage source, so many connections for them, right. So, we should try to generate this VBB in terms of VCC, this is our objective. So, actual circuit, how we can do that? This R1 and R2 we can generate VBB. What is this circuit? R1 and R2, this is termed as voltage divider. Okay. So, what is my objective? To generate. How we can do that? This is R1 and this should be my VBB. So, what is VBB now? VCC into R1 by. So, now you see my circuit becomes simpler in terms of I have reduced one voltage source. This supply is supplying both the collector as well as both the base. How? This value is bigger, this value is smaller. What is your objective? How much voltage you roughly need? Around 0.7 above V. If V is, suppose V is say 2 volt. So, you need 2 volt plus 0.7. That way you should do, na? Right? Suppose emitter is 0. So, how much you need? Only 0.7. Suppose emitter is not at 0. In this case emitter is not at 0, right? Some IR drop is there. So, you calculate IC, you calculate IE, you will get IERE. Then you should target, okay, my base voltage should be this VB roughly 0.7, right, and this emitter voltage is this voltage. So, if you follow KVL here, so VB is equal to VBE plus IERE, isn't it? So, this potential divider can generate my base voltage. Okay. So, I have removed one voltage source, done, input side is done. What is the meaning of DC biasing here? To find out the proper values of R1 and R2, so that you arrive a proper value of VBB, so that base emitter junction is at forward bias. Then what is your objective? To find out the first objective was to find out VBE, right, then find out IB, then find out IC, then find out VC. Next, to find out IC, what is your equation? VCC is known. Suppose you have to find out this VCE, then VCC minus VC by RC, you will get IC. So, next target is to find out the value of RC. If you can find out the value of RC, IC will be known. Next target is to find out this loop, VCE, or this complete loop. VCC is equal to ICRC plus VCE plus IERE. So, you see, only one equation you will be have to do, either KCL or KVL. So, where is my KVL? This point. So, from this onwards up to 0. From this onwards, what are the potential? VBE plus this drop. If we start from this potential, I will come down to up to 0, ICRC plus VC plus IERE. Now, see, some capacitor are drawn there. We discussed this, now. They are known as the coupling capacitor, right, or bypass capacitor. So, what is the job of this capacitor? To couple the AC signal, and why it is placed? We discussed this. Now, I have properly find out the VBB, right, and I do not want to disturb this, I do not want to disturb this Q point, right. So, this AC source, it should start from 0, right, and AC signal, but I do not know, it may have a DC portion and all the AC signal also, I am not sure. So, the job of this coupling capacitor, this is a coupling capacitor at the input side, right. The job of this coupling capacitor is to pass the AC, but block the DC, because DC is already I have properly biased. I have taken pain to calculate the R1 and R2 to properly bias this. Now, I do not want to get it disturbed. If it is disturbed, what will happen? The Q point may vary and it may come this position, and one side will be short, other side will be big, right. One side my room is less, other side my room is. So, my output swing is not symmetrical, it is asymmetrical. So, I do not want to disturb that. So, you see, what should be your ideal value? C value, large or small? It should be large enough so that it behaves like a blocking the DC, and at that frequency it behaves like a short. What is the impedance of a capacitance? Right. So, if your omega is high, what will happen? This impedance will go down, right. So, if omega is equal to very large, so this will go close to 0, 0 means it will behave like a short circuit. So, where it should behave like a 0? The frequency of interest, this signal should have a frequency, na? Suppose you have bought from an amplifier from market and you know that your AC signal is say 10 megahertz, right. So, you should choose this C value such a way, if you multiply it with 10 megahertz, it should give a very small resistance, so that it is close to 0. How should you choose the C value? This should be your guideline, that what is my, suppose your signal is very small, say 1 kilohertz, then you have to make it bigger again even. Okay. So, this C value you should choose, so that at the frequency of interest this should be short, at DC value it should be open, but at the frequency of interest it should behave like a short. So, by default it is very large, microfarad or something. In microfarad means quite big capacitor. Okay. So, this is my input side coupling capacitor. Similarly, at the output side also, in the output side we are interested to pass out the amplified signal, right. Okay. And we can have a, this stage may drive another stage. We have seen that amplifiers generally they are cascaded, right. So, as I do not want to disturb my DC at the input side, this could be connected to another amplifier. So, similar way I may not want to disturb the DC of the DC biasing of the next stage. So, this is my coupling capacitor at the output. So, the purpose of this and these are same, to couple input stage with another stage. This is my input source and this is to couple with the output to the next stage. I do not know what the next stage is, think of that same inverter is there, right. So, I will be also thinking that this DC should not be disturbed. So, you think this cap and this cap as if doing the same thing. Okay. So, coupling capacitor, why we are using, clear. Now, what is this cap is doing? See, this is not coupling with something, any source is there? No. If this is AC signal, then this capacitor will be like a short circuit. So, this resistance should be there or not? It should be short, right. So, if it is short, what is this potential then? Then you will think like this is my ground, right. Okay. You see what we are doing. If we have this emitter resistance, this is our ground, right, but this potential is our IE-RE. Now, this if we use this capacitance, then what it is doing? It is bypassing this IE-RE value, right. Bypassing means, suppose you have a longer path and you have a shortcut path and you will take the shortcut path to reach quickly, right. So, this path is bypass this IE-RE drop and as if there is no drop, ground, right, 0, this emitter potential is at 0. So, this cap is known as the bypass capacitor. This capacitor is known as the coupling capacitor, but this capacitor is known as the bypass capacitor. So, you just remember this term or emitter capacitance. Sometimes this we are also, this is connected with emitter junction, na? Emitter capacitance or bypass capacitor. So, what it is doing, as if AC wise this is making the emitter junctions shorted to ground. Why, and we will discuss this point later, we will come to this point, you remember this, why we should do that I will come and discuss later. So, okay about the purpose of this two cap, one is coupling cap which is used to couple the AC sources and block the DC sources. Why? Because DC is already defined, I do not want to disturb it. My purpose is to just to connect the AC signal, and bypass cap is to bypass the IE-RE drop and getting it to 0. Okay. So, we will stop here and we will start from this in next class.